All right, today we're applying the principles of force and torque to a system of two blocks that are hanging from a pulley. Now that pulley is fixed on an axle, so it's free to rotate, and these two blocks are attached to the pulley so that one block is trying to rotate the pulley in one direction, and the other block is trying to rotate the pulley in the other direction. And today I'm going to show you how to calculate the masses, or in this case, this second mass, M2 here, in order to keep the system in balance. And I'm also going to show you how to calculate the acceleration of this system if one side is too heavy. Now the key in this problem is that these two blocks are attached to the pulley at two different radii. That is to say, this 10 kilogram block is attached to the outer edge of this pulley at a radius of 0.3 meters. But our unknown mass here is attached to the pulley at a radius of 0.2 meters. And the reason that's important is because even if these two masses were the same, they would be putting different amounts of torque on this pulley, causing it to rotate. Now the first thing I want to walk you through today is just how large we have to make this value of M2 in order to keep this pulley from rotating. Now when I say we're going to keep the pulley from rotating, really what I mean is I want to keep this pulley in what's called static equilibrium. Now in order for an object to remain in static equilibrium, there's several conditions that have to be met. The first condition is that the object can't rotate, and that is to say the sum of all torques on that object is 0. This little Greek letter tau right here, that's what we use for torque. And the next condition for static equilibrium is that the object can't translate, or meaning it can't move in a straight line, either up or down or left or right. That is to say, the sum of all forces on that object in any particular axis needs to add up to 0. So if we're trying to keep this pulley from rotating, that means we're going to need to be looking at the sum of all torques that are acting on this pulley. Now torque is given by the equation Rf sine theta. That is to say, torque is the result of a force, that's our F, acting at some radius on some object, R being the radius. Really, most people think of this radius really as leverage. A long lever would have a large radius, meaning it would provide a lot of torque. Now theta is the angle between the force and the radius. Realize those are both vectors, so there's a direction between that force vector and the radius vector. Now the nice thing for us in this problem with the pulley is that anytime we wrap a string around a pulley, the string will fall tangent to the edge of the pulley, meaning the force by the string is always going to be at a right angle to the radius vector, meaning that this sine theta term for a string wrapped around a pulley is always going to be the sine of 90 degrees, which works out to be 1. And so using this equation for torque, and understanding that in order to keep this pulley static, the sum of all torques, or the total torque on that pulley, needs to equal 0. There's two things that are providing torque on this pulley. We have our mass hanging from the left and our mass hanging from the right. And they're acting in different directions. This mass on the left is trying to rotate the pulley counterclockwise, and the mass on the right is trying to rotate the pulley clockwise. Now, it really doesn't matter which way you choose to call the positive direction. I'm going to say in this problem that the positive direction is clockwise. So looking at the sum of all torques, what we really have is our torque to the right in the positive direction. That is the torque by this unknown mass M2 hanging down here, competing with the torque to the left. I'm going to say that's in the negative direction because this 10 kilogram mass is trying to rotate the pulley counterclockwise. Now, pulling this torque to the left over the other side of the equals sign here, we see that these two torques need to be equal to one another in order to keep this pulley from rotating. Really, the two torques are balanced. Now that doesn't mean our two masses are going to be balanced because they're acting at two different radii. But if we go back over here, using our equation for torque, the torque on the left is going to be the radius. That's the distance from the pivot to where the string is attached to the pulley. That's a distance of 0.3. multiplied by the force or the tension in this string. Now because this mass is just sitting here in equilibrium, the tension in this string is going to be equal to the weight of the block. That is 10 times 9.8. So we find that the torque by this left mass is 29.4 Newton meters. Newton meters being the units of torque. Now on the right side, we have a bit of an unknown here, this M2. That's what we're trying to solve for. Now we do know that this string is going to be pulling on the pulley at a radius of 0.2 meters. So plugging that in, we're going to have the torque on the right is 0.2 multiplied by the tension in this string, which is equal to the weight in this block. So we're going to have the mass, m2, times 9.8. So taking our torque from the left side and the right side, and then subbing those two known values into our equation up here, or really understanding that those two values have to be equal, we can say 29.4 Newton meters is equal to 0.2 times m2 times 9.8. And we can solve for this value m2. We find that's 15 kilograms. So what this means is, if this mass right here, m2, was 15 kilograms, then this whole system is just going to sit in static equilibrium. Even though the two masses have different values, because they're acting on the pulley at different radii, their torques are going to cancel each other out, and nothing's going to move. So that brings us to the next question, and that is, what happens if m2 over here is greater than 15 kilograms? Let's say we make it 20 kilograms. Now, of course, if we no longer meet the conditions for static equilibrium, or really we're not keeping everything balanced on our pulley here, these masses are going to accelerate. So really the question is, at what rate are the two masses going to accelerate? Now, there's a key concept in this entire problem, and this is where I see people go wrong with this, and probably why you're watching this video right now. These two blocks do not move the same amount. You see, if this block moves down, it's going to turn the pulley a certain amount, and as a result, this block will move up. But because the two blocks are attached to the pulley at different radii, they're going to move different amounts. I mean, if you think of the pulley like a spool where string is either being wound onto the pulley or off of the pulley, if this pulley rotates around once, there's going to be less string unspooled here to lower this heavy block than there is string that's wound onto the pulley over here on this larger radius. And so as we work through this solution, we have to be very, very careful to keep in mind that these two masses do not move the same amount. Now, to solve this problem, we're going to turn both to Newton's second law in a straight line, that is F equals ma, and we're also going to have to deal with Newton's second law effectively in a circle. And that is to say that the sum of all torques on any object, in this case the pulley, is going to be equal to that object's inertia times its angular acceleration. Now, rotational inertia is really a measurement of how easy it is, or hard it is, to get an object to rotate. You can think of it as the angular version of mass. Mass is really a measurement of how hard it is to get something to move in a straight line. Or to put it simply, inertia is simply the rotational version of mass. Alpha here, that's our angular acceleration. You see, because some of these blocks are moving in a straight line, we can talk about their linear acceleration. But this pulley is going to be rotating and actually speeding up in a circle, so we're going to be talking about its angular acceleration. And the goal here is to simply set up a system of equations that we're going to be able to relate to one another in order to solve for the acceleration of each of these objects. So I want to start with the left block here. You see, applying Newton's second law to the left block, we have the tension in this left string acting upward on the block, and the weight of the block acting downward. Now I'm going to do this in variables because chances are you're stuck on your homework here. Turn into YouTube for help. And rather than me putting in at 10 kilograms here, I'm just going to say this is the mass on the left. So we've got the tension in the left minus the weight of our left block. That's m on the left times g. And realize that that is the net force acting on this block. So that's causing the left block to accelerate at some rate. I'm going to call that AL, or the acceleration of the left block. And it's important to keep all these little subscripts straight here, because we have to keep track of the fact that what's happening on the left, especially with acceleration, is not the same as what's happening on the right. Now moving on to the right block. Again, we're going to apply Newton's second law. And looking at this block, we have two forces. There's the weight of the right block, and there's the tension in the string. And what we have to be careful about here is the positive direction. You see, in this case over here with this block, we said up was positive and down was negative. Well, that upward motion of this block over here correlates to the downward motion of this block here, meaning we're actually going to say downward is positive for this block. So in applying these two forces to Newton's second law, we're actually going to have the mass on the right times g, that's its weight, minus the tension in the right string. And that's going to cause that mass on the right to accelerate at some rate. We're going to call that AR. And again, remember, because these two blocks don't move the same amount, they have different accelerations. You've got to keep this acceleration on the left separate in your head from the acceleration on the right. That's why we're showing AL and AR. Now last we have the pulley. Now the pulley isn't moving in a straight line, so we're not going to apply Newton's second law, or F equals ma, to the pulley. We're going to apply the rotational version of that equation, or the sum of all torques equals I alpha, to the pulley. Now looking just at the pulley, there's two things providing torque. We have the tension in the right string, acting at this radius, and the tension in the left string, acting at a different radius. And they're each providing torque in competing directions. Now going back to our convention of positive direction, we said this block moving up was positive and this block moving down was positive. And that all correlates to the clockwise rotation of this pulley being positive. So when we look at the sum of all torques acting on this pulley, really what we have is the torque from this tension right here. I'm going to call that the tension on the right multiplied by the radius on the right minus the torque from the string over here. That is the tension on the left acting at a radius. I'm going to call RL. And those are causing the inertia of the pulley to go through some angular acceleration. And so what we have here is a system of equations. And what we're going to do, since physically it's this pulley that's sort of tying everything together, we're going to take the two equations for our blocks here and substitute them into this equation. But you'll see we have way too many unknowns at this point. We don't know either of the tensions or the accelerations. And so we ultimately have too many unknowns. What we have to somehow do is relate the angular acceleration of this pulley to the linear motion of our two blocks. Now we can relate linear acceleration to angular acceleration through the equation A is equal to R alpha. So on the right side of this pulley, we can say the acceleration of the right block is equal to R alpha, and the acceleration on the left is equal to R on the left alpha. So what we have now is a system of equations. And I understand that 5 equations and 5 unknowns might seem a bit daunting. I'm going to walk you through that. But realize, at this point, we're done the physics. And all we have left is some math, or really just algebra, to work through in order to solve the acceleration of this system. So pushing all this stuff over here, we're going to need all the room we can get. I want to start with what we called equation 3 over here. That is the pulley. And we're just going to kind of fit in everything else into that equation. So the first thing we're going to do is sub in our rearranged equations for tensions from each of these blocks. So that's going to go here for the tension on the right and here for the tension on the left. Now you'll notice we've got linear acceleration on the left half of this equality and angular acceleration over here. So we're going to go down here and we're going to sub in these equations 4 and 5 for angular accelerations up here. So we've got alpha everywhere. Remember, alpha is the angular acceleration of this pulley that's off the page now. It's the angular acceleration of the pulley once everything's moving. So we're going to do some algebra and then even more algebra. And what it leaves us with is an equation. So we get this equation for alpha that relates the two masses to the inertia of the pulley as well as the two radii of the pulley. Now, if you're working through a problem on your homework, this is the formula you actually want to be using, but I'm going to pretend some people are emotionally invested in our pulley that we're dealing with over here. So plugging in the numbers from our pulley, our original problem, we'd find the angular acceleration of the pulley is 3.62 radians per second squared. And then going back and relating linear to angular accelerations at the two different radii where the string's attached, we can find the acceleration of each block. We find the acceleration of the block on the right, over here, is 0.73 meters per second squared, and the acceleration of the block on the left is 1.09 meters per second squared. So I hope you found this useful. And on that note, that's all for now.